Okay, good morning everyone. So I will soon share the screen. Yeah, this is where we had stopped the last class. So there we had alluded to many useful quantities can be obtained fairly explicitly in the case of time homogeneous Poisson processes. So we will look at first of such examples is waiting times and interarrival times. Remember that Poisson process with arrival rate lambda, the n of n at t, it counts the number of events which have occurred or arrived during the time period 0 to t. So now we look at the times of arrivals of these events. So in that direction, for any integer, positive integer n, we define w sub n as the infimum t greater than or equal to 0, nt equal to n. That is the first time t, of course, t greater than or equal to 0, such that n of t is equal to little m, which means at that, if supposing this happens at tn, n at tn is n, I mean n at t sub n is n, and if you go slightly to the left of t sub n, it will be n minus 1. So that is the meaning of infimum. That is the, I mean, intuitively it is the minimum, but when we are dealing with the continuum of values, it is always better to denote that as infimum. And since all these guys are assumed to be non-negative, the infimum exists. So W sub n is, it makes sense in the sense that it can possibly be infinite. We don't know yet. In other words, n of t just may not even become n. Theoretically, such a possibility is there. But soon you will see. Okay. We also define a sub 1 as w1 and a sub n as wn minus wn minus 1. So this is, that will go to the next slide. So this will be the time at which the nth event happens. And of course, the first event happening is same thing as the arrival of the first event. A sub n is the time lag between the n minus 1th arrival and nth arrival. So this is the time one has to wait after the n minus 1th arrival up to the nth arrival. Some kind of a corresponding things you have seen in the discrete case. When you have Bernoulli trials, then the first time the first success occurs, that would correspond to W1 as well as A1. And W1 corresponds to the nth time, the time of nth success. So A sub n would correspond to the number of trials between n minus 1th success and nth success. So this is a natural object which you can associate with the Poisson process. Note it down if you want. Okay. So as is fairly obvious and intuitive, of course, all these things are going to be random variables, taking values in non-negative integers. So these will be random variables taking values on 0 to infinity. This need not be an integer. This little n is the integer. Wn can take any value between 0 and infinity. Similarly with the AIs. Sorry, I just made a slip of the tongue, or rather error. These are non-negative random variables, not integer value. Okay. The random time Wn is called the waiting time until the arrival of nth event. That is quite natural thing to call it. And as we had seen earlier, the random time A sub n is the time between the n minus 1th and nth events. So you have this sequence A sub n, n greater than or equal to 1. That sequence is called a sequence of inter-arrival times. Inter-arrival time meaning the waiting time or the time between two successive arrivals. So our objective is to see if we can say something about the distributions of these guys. Note that this Wn will be, as n varies, it will be non-decreasing. In the sense, W1 would be less than or equal to W2, and W2 will be less than or equal to W3, and so on. Actually, it will be soon be an exercise for you to see that W2 will be strictly less than W2. W1 is strictly less than W2. And things like that. And W1 will be strictly positive. Yeah. Please note it down if you want to. Since n0 is 0, note that the first arrival can occur only at some time t greater than 0. Because if W1 happens to be 0, that would contradict this. And similarly, as we are assuming that, one of the postulates of the Poisson process is that the probability of two or more arrivals in a very, very short span of time is very, very negligible. It is of this small order h. That means that these Wi's are strictly increasing. That is, probability of 0 strictly less than W1, strictly less than W2, strictly less than W3, etc. is equal to 1. And this in particular implies probability of A sub j strictly positive is 1. Each A sub j inter-arrival time is strictly greater than 0 with probability 1 for every j. Please note it. Okay. Now we will find the distribution of W1. Of course, that is since W1 is equal to A1, that is also the distribution of A1. So what this result says is that, see, A1 as well as W1, they take values in 0 to infinity in the positive part of the real line. So probability of A1 taking a value in an open interval little ab is precisely integral a to b lambda times e to the power minus lambda s ds for any ab interval contained in 0 infinity. And we know that this function is the probability density function of the exponential random variable with parameter lambda. So A1, of course, as well as W1 has the exponential distribution with parameter lambda. In the discrete case, similarly, the role was played by the geometric distribution. The success failure experiment, the trial at which the first success used to appear, or rather the number of failures before the first success, we have seen that as a geometric distribution. So that's a discrete distribution. Here, the exponential distribution is the continuous. So the geometric distribution, exponential distributions, etc., are also sometimes called waiting time distributions. Okay, let's proof is fairly simple. So for any t greater than 0, probability that a sub 1 strictly greater than t, and of course that is same thing as probability w1 strictly greater than t, which means during the interval 0 to t closed interval, there is no arrival. And that is same thing as saying probability of nt equal to 0. And you look at that theorem which we proved the last class, theorem 1, I think is called. So nt has an exponential distribution with parameter lambda. So probability nt equal to 0 is precisely this. So this statement means probability a sub 1 strictly less than or equal to t is 1 minus this. And as you know, this is the distribution function of the exponential distribution with parameter lambda. Or even other words, you can write 1 minus e to the power minus lambda t as this. So this completes the proof. It's a very, very simple exercise. Okay. Now, before we go further, certain things which we observe. So, probability of W1 taking the value infinity is 0. And of course, as well as probability W2 taking the value infinity is also 0. Of course, the second statement would obviously imply the first statement. So to show this, you observe that probability W2 equal to infinity is same thing as this. Nt never increasing, does not go beyond 1, whatever t might be. And you know this quantity. So next, we want to look at or find the joint distribution of W1, W2. You know that W1 is less than W2. Okay, so that itself gives you some information. You can intuitively expect, and of course, both these things are positive. You have an idea about the set in R2 where this random variable will take value. Yeah, note it down if you want to. Okay. So this result says the two-dimensional random variable W1, W2 has the probability density function given by the density function at a point S1, S2 is lambda squared times e to the power minus lambda S2 if this happens. 0 less than S1, less than S2, less than infinity. I mean, this equation I'm referring to it by O dot with the subscript 2. This symbol, I think, is O dot. There is an O and inside there is a dot. And it is 0 outside of this set. Yeah, before we proceed further, a small diagram I will show you, which will sort of tell you, give the intuition behind the whole thing. So we will stop sharing the screen now. Can you see the screen?
Yes, sir.
So this is the two-dimensional space. I am showing only here the first quadrant. And this shaded portion, which we have going to denote by G2, is that set where S1 is less than S2. So this is the horizontal axis is the T1 axis and the vertical axis is the T2 axis. So this set is T1 less than T2, and of course both of them are in the positive set. So what we are going to do is we are going to find the probability that the two-dimensional random variable W1, W2 taking value in a rectangle which is strictly contained in this G2. So let us say the rectangle is of the form A1, B1, open interval A1, B1, cross A2, B2. I will write it. So this rectangle So this rectangle is A1, B1 times A2, B2. That is the rectangle. Here is the A1, B1 and A2, B2. So now this rectangle has 4 corners. Look at this corner. See, the entire rectangle is going to be inside that G2. That is the open part of the rectangle. So if the closure itself also is inside that, then this point whose coordinates would be x coordinate is B1, y coordinate is A2, B1, A2. So B1, A2, if it belongs to the G2, B1 will be strictly less than A2. But our requirement is only the open rectangle should be completely inside that. So this point can possibly be on the line x equal to y. So that is why we write this, where have we written? Here. Yeah, B1 less than or equal to A2. Please note it down because that will make what we are going to say a little later clear. All right. So now we will go back to the screen and continue. Yeah. So I suppose now you can see the screen.
Yes, sir.
So please note it down. All right. So now because of that remark, this remark here, the second part of the remark, and this exercise, because of this, we consider this region. That is, we expect that the probability that the two-dimensional random variable W1, W2 taking value in G2 is going to be 1 because W2 is strictly less than infinity. That's what we have seen. That is probability W2 equal to infinity is 0. Therefore, probability W2 strictly less than infinity is 1. So we consider this region. This is a triangular region in R2. So when you are dealing with a triangular region, you have to be quite careful when you change the order of integration and things like that. Just like if you involve that is in discrete, the summation of series also, you have to exercise care in such cases. So we have the expression for this is our candidate expression for the density function. So first, as an exercise for you, verify that this happens. Note it down if you want. So this, the integral for R2, I am denoting the two-dimensional integral that is on R2. So that ds2, ds1. And similarly here. If I try to type two integral signs, then that G2 could not be put. I mean, it will be either in between the two things which might be associated with the left one, or if I write it after both the things, it will be associated with the right one. So I have just put integral R2 or integral G2, integral over G2. Yeah, now we will proceed. So as I mentioned earlier, so we consider a rectangle A1, B1 cross A2, B2, which is completely contained in G2. Then, as we have seen in that diagram, that small sketch, you can verify that, of course, A1 can possibly be 0 and A0 less than or equal to A1, strictly less than B1. B1 can possibly be equal.
Sir,
Yeah.
shouldn't it be B1 strictly less than A2?
No. See, B1, see A2, B1, did you take down that diagram which I noted, gave you?
Yeah.
In that, we want only this open.
But the line is not included in G2, right? Line is not contained in G2.
Not included in G2.
Yeah.
But this thing, if the one of the points, you draw a rectangle like this, okay? When you draw, you cannot draw an open rectangle, right? Closed rectangle only you can draw.
Correct.
So that one of the boundary points, which is that B1, A2 can possibly be on the diagonal line.
Okay.
That is why here there is a possibility of B1 being equal to A2. If that figure which I showed you, the whole rectangle, including the boundary, was inside G2. So there, B1, B2, B1, comma A2 was also inside the G2. It was strictly less than. But in principle, B1 possibly being equal to A2 cannot be ruled out, because the boundary point of this rectangle, this can be on the line x equal to y. Take some simple examples. 1, 2 and 2, 3. Okay, the x-axis you take 1, 2, and y-axis you take 2, 3. So the point corresponding to B1, A2 will be 2, 2. Okay, is it clear?
Yes, sir.
Yeah. Good. So now we, in the next slide, will have a series of equations, and in that we will be using the independent increment property N3, and of course the conclusion that that equation which we had called by denoted by asterisk in theorem 1. Using that, one can verify the following. Probability W1, W2, taking values in this open rectangle A1, B1 cross A2, B2 is equal to A1 less than W1 should be in A1, B1, W2 should be in this, which means A1 less than W1 less than B1 and A2 less than W2 less than B2. That B2 is sort of has gone out of the thing. So what does this mean? This means W1 is in A1, B1, which means the first arrival has been in this interval. So up to time A1, there has been no arrival. So n of A1 equal to 0. And since the first arrival has taken place here, and the second one is happening only here, the number of arrivals between A1 and B1, which is nB1 minus nA1, is exactly equal to 1. And between B1 and A2, there has been no arrival. Of course, if B1 is equal to A2, this is simple. So between B1 and A2, there is no arrival. So that is equal to 0. And what about the second arrival is in the interval A2, B2? We are not saying only the second arrival is here. This interval can even have 5 arrivals. So this event is same thing as NA1 equal to 1, NB1 minus NA1 equal to 1, sorry, NA1 equal to 0, NB1 minus NA1 equal to 1, NA2 minus NB1 equal to 0, and NB2 minus NA2 is greater than or equal to 1. W2 is in A2, B2 means the second arrival, at least the second arrival is here. There may be more. So this equality is just by realizing what this event actually means. Now you use the independence increment property. This is the probability of the intersection of all these guys, those 4 events, which are concerned disjoint intervals. So this is probability NA1 equal to 0, probability NB1 minus NA1 equal to 1, probability NA2 minus NB1 equal to 0, multiplied with probability NB2 minus NA2 is greater than or equal to 1. By that theorem and the equation asterisk in 1, we know that NA1 has a Poisson distribution with parameter A1. So probability NA1 equal to 0 is precisely this term, e to the power minus lambda times A1. And from that same result, we know that NB1 minus NA1 has a Poisson distribution with parameter lambda times B1 minus A1. And that random variable taking the value 1 is precisely lambda times B1 minus A1 multiplied with e to the power minus lambda B1 minus A1, that is. And similarly here, it is this. And now this event, this is probability NB2 minus NA2 greater than or equal to 1. So that is the exponential random variable with parameter lambda times B2 minus A2 taking a value of 1 or greater than that. So that is same thing as 1 minus probability that this guy equal to 0. And that probability is precisely 1 minus e to the power minus lambda times B2 minus A2. So convince yourself by looking at that theorem and the statement and what this Poisson distribution means at the points 0, 1, and things like that. So you can do cancellations here, the exponential terms. And after that, what survives is lambda times B1 minus A1 multiplied with e to the power minus lambda A2 minus e to the power minus lambda B2. This term you can write as integral A2 to B2 lambda times e to the power minus lambda S2 ds2. And now this term B1 minus A1 you write as integral A1 to B1 ds1. So that is equal to integral from A1 to B1, integral A2 to B2, lambda squared e multiplied with e to the power minus lambda S2 ds2 ds1. Note it down. I mean, this is the mainly the crux of the argument in this kind of analysis. Okay, note it down. Since this equation double asterisk holds for every rectangle contained in G2, the required result follows that O dot 2. This is the required result. So we have expressed that probability taking value in the open rectangle as the integral of this guy over that rectangle. Just like in the one-dimensional case, yeah, from this expression we could say that this is the PDF of A1. Because the one-dimensional case, because of this, one can say that this expression is valid even if this set, instead of being an open set, it can be union of two open sets or a closed set and things like that. Okay. Yeah. So we have got this expression that is equal to this, and this is precisely your FW1, W2 at S1, S2. So basically any nice set in G2 can be expressed in some way or other, union of countable number of disjoint rectangles, or sort of just like you have take a graph paper, any region you write, then you can view that area of the grass, that region as the sum total of the smaller and smaller squares or rectangles inside that, and make the grid thing become smaller and smaller, you get better approximation. And measure theoretically, one says that this is because the rectangles contained in G2 generate the Borel sigma algebra of G2. That is, all the nice useful subsets of G2 can be obtained from our knowledge of rectangles. So those of you who know measure theory, you can just appeal to this result and then conclude that result. Others, you just start up, take it this thing that any nice set can be approximated by union of such rectangles. Any nice set contained in G2 okay. So that proves this important result. Yeah. So this result is our key to understand W1, W2, and similar analysis will be extended to W1, W2 to Wn and things like that. Okay. So from this result, one can get hold of the probability density function of A1, A2. So using the result concerning the PDF of W1, W2, we want to get hold of the PDF of A1, A2. So note that A1 is same thing as W1. And now you can write A2 as W2 minus W1. So basically A1, A2 is a linear transformation of W1, W2. That is what we are going to state in the next. So this where we will stop. Yeah, that will take it up in the next class. That part that the discussion is slightly more. So if you have any doubt in today's thing, especially the two-dimensional thing, W1, W2, please, you can ask me. Otherwise, we will stop here for the day. Okay. So the next class we will see the n-dimensional case. That the two-dimensional thing we will finish off. It requires another 5 minutes or so. Then the n-dimensional case and so. By the way, what do you expect will happen to A1 and A2? A1 you already know. Yes, come on, guess. Try to take a guess. Even if the guess is wrong, it doesn't matter.
Independent.
Yes. Why do you say that?
Inter-arrival times again. So exponential has memoryless property.
Okay, but I expected that is not the quizmaster's answer.
So your question is why are A1 and A2 independent, or your question is why are A1 and A2 independent, or
sort of, yeah, that is the crux of the question.
Yeah, so I think like this again, independent increments we can.
You are right, but I want again, that is not the quizmaster's answer. Okay, I will sort of tell you that. I was telling that this is we have seen similar situation in success failure experiments, right?
Yes.
There we have seen that the number of tosses between two successive heads, number of failures between two successive heads and so on, if you consider, they are independent random.
Oh, right. They have the same distribution as
geometry.
Yeah.
So this is going to be analog of that.
Okay.
Good, good. So it is always sometimes to try to make some kind of a guess, especially if you see analogy with something which you have seen earlier. So that sort of gives you a feeling that that is what you would expect to happen. And once you think that that is what is expected to happen, then the details of the proof you can follow very easily. Okay. So at times become a bit adventurous and try to take a guess. Okay. It doesn't matter if it goes wrong, then you know that at least your knowledge increases, at least that answer is wrong. Okay. Okay. We will stop here for the day. And
Thank you, sir.
yeah, see you on Wednesday. Stay safe and take care.